Now it's red. Anyway. Okay, now I'm going to take you back to Bohr. And Bohr's idea of the atom was a planetary vision. Because the solar system had planets revolving around the sun, and Bohr thought, oh, well, this is perfect. We're going to have electrons revolving around the nucleus. And electrons can only be on those orbitals, nowhere else, no exceptions. And the orbitals in the closest to the nucleus were the most stable because the protons are positive, electrons are negative. So, and then by going around fast enough, it kept it from spiraling in. Additionally, we're not going to cover this on Saturday, but Bohr's atom also said that electrons can jump from one orbital to the next and come back. And that's how fluorescent lights work. That's how lasers work and LEDs and all that stuff. Bohr. And he was Einstein's buddy. And during World War I, in the beginning, they wanted all these scientists come to work for the army and invent gas. And Einstein said no, and Bohr said yes. Bohr died of poker, Einstein didn't. So yay for Einstein. Nerve agents, mustard gas, oh, it's a horrible way to die. Horrible. It takes hours to die. And you're in excruciating pain. And your lungs fill up with fluid and you're just. Anyway, Bohr's atom. Okay. So we've got this planetary model where we have electrons who are circling around. Now, along came quantum mechanics. Quantum mechanics said, this doesn't work. One, there's for the electrons to flow around in orbitals, it requires energy because every time you're in an orbital, the electron has to curve a little bit to stay in orbital. That's called angular momentum, and angular momentum requires energy. So unless energy is supplied to the electron, it just spirals in. So that's the main thing with Bohr's model. Also, it's two-dimensional, not three-dimensional. Okay, so let's look at lithium. Lithium has 3 electrons. Its atomic number is 3. Located right here. Oops. Okay, so let's look at the Bohr atom in more detail now. Okay, we're looking at the first orbital. Now, lithium has to spread out those 3 electrons over all the orbital potentials. So the closest one is the most stable, so it's going to fill first. So we can put 2 electrons in that first orbital. No more can fit in there. So we have to go to the next one out. Now that one can fill or have 8 electrons in it. And the next one out can have 18, and it just because the orbitals are bigger and hold more electrons. That was his thinking. Okay. Now every element up there, up to 118, has electronic configurations, just like it just did for lithium. Now, lithium was very simple. Uranium, for example, has 92 electrons. I mean, that's a lot of circles. It was very cumbersome to approach it this way. So they've invented a numbering and lettering system. Okay, so what we have is we have a number, a letter, and an exponent. Okay, the first number the coefficient, is called a shell. And on a periodic table, so I just need to. No, there's like periodic table right there. Okay, on the periodic table, the shell refers to this number here. So in shell 1, that contains hydrogen and helium. Shell 2 contains lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. Okay, so getting back to this. So that's what shell we're talking about. Now remember, lithium has 3 electrons. Shell 1 only accounts for 2 of those. So some of the electrons are in shell 2 also. So we have to have another one of these over here to account for that 3rd electron. Okay, parts of the shell are subdivided into subshells, all except for shell 1. Shell 2, 3, all the way up to 7 have multiple subshells, and they have letters. So this subshell here is called S. And they don't really correspond to anything that I'm aware of. They could have some Russian meaning or German meaning or something like that. I don't know. And then S for me corresponds to sphere because it's the orbital is spherical. But that's the only one that makes sense to me. Okay, in the middle here are D's, and these are P's over here on the right, and F's on the bottom. By the way, on the tests where you had to identify parts of the periodic table, I swear half of you missed metals. And you forgot to include all the metals. You put some of the metals, but not all of them. That was the biggest mistake. Okay, so metals take up half of P, D, S, and F. In other words, only the P, half the P's over here, the only thing that are not metals. And then the metalloids too. Everyone got the metalloids. Not everyone got the metals. Okay. All right, so that's part of the configuration. And then we have the 3rd electron. That's in shell 2. So here's lithium, so it occupies part of shell 2. And now let's look at, so this is the electron, oh, and then here is, the exponent is how many electrons are in that subshell. So the sum of the exponents have to be equal to the number of total electrons in the atom. So what this does, this accounts for every single electron in that atom. Uranium has 92. So uranium's electronic configuration is this long. And that goes up all the way up to 118. 118 electrons are counted for. Now, some of them are core electrons and other ones are valence electrons. So valence electrons come up a lot in chemistry. So valence electron or electrons are the outermost orbit. Core is everything inward. And the core electrons are extremely stable. They're like stable squared. I mean, they're extremely stable. So they never interact with any reactions because of the stability of those inner core electrons. Valence electrons are the opposite. They're flaky as heck. They come and go. They're not stable at all. And that's the reason that atoms form bonds, because they can take those flaky valence electrons and put them in a more stable state by hooking up. Now, there's a whole discipline in chemistry called physical chemistry. It's the hardest class I've ever taken. You have to take a whole year of it, at least Davis. I don't know what it is exactly. And it's horrible. That's when your calculus comes into play, is in physical chemistry. I'm talking about doing like triple integrals, differential equations, you know. So, okay. So really, frequently electronic configurations are only of the valence electrons. And I'm going to show you the way that's done. Okay, so does this make sense? Now, it's awkward. I'm here to tell you, I think it's awkward as heck, but that's the way it is. Now, what's important about doing electronic configurations, you can figure out why an ion forms. It's for stability reasons, right? I'm going to show you how the stability comes into play with an ion. Remember, ions can be positive or negative. Positive ones lose electrons, negative ones gain electrons. Okay, so let's take another example. Let's do, well, let me give you another example. I'm going to do uranium for you. And you don't write this down unless you want to write it down. But okay, this is what uranium looks like. And remember, 92 electrons. So it's okay. So that's uranium. Pretty wild, huh? Now, if you count the exponents, there's 92 of them. 92 in all the exits. So you're not going to be able or want to, or let me back up. You're not going to be responsible for doing electronic configurations like this in terms of the complexity. Now, your 1A class and your 2A class, particularly 1A, you will be doing a lot of these in 1A. In 2A, you may do it kind of like we're doing in here, because it's health related, and it depends on who's teaching it also. The way I teach 2A is like we're doing in here, not that. Okay, so that's uranium. Let's do something more civilized. Let's look at now this is one of the reasons carbon. Well, let me do carbon, and there's a conundrum with carbon. Okay, so carbon has 6 electrons, 2 core, 4 valence. We're going to go two electrons are going to go in shell 1, block S, or subshell S. Okay, that accounts for 4 of the 6. We need 2 more. So that's going to be in the P. So that's the electronic configuration for carbon. Now let me show you the way my student invented. Now she had 3 kids, and the oldest one I think was 7 or 8. And so she had a lot of stuff going on. And her house was very organized, very non-cluttered. I mean, I have no kids at my house. It's cluttering. Okay, so here's carbon. Now, the way she tells it to her students, her 2 T's, is we're going to take a little ride through the periodic table. Now remember, she's used to telling stories to her children. So this is what we're going to take a ride through the periodic table. And as we go, we're going to be placing down markers as we go. Okay, first thing is find your element. Okay, in this case, it's right there. So we're going to take the ride starting in hydrogen and go to carbon. Okay, so as we go, we're going to be writing down the electrons along the way. We're going to go 1s2, 2s2. Excuse me, 1s1, 1s2, 2s2, 2p1, 2. Now, your book doesn't do it that way. Your book makes you memorize this goofy diagonal thing, and your next teacher will too. But you have to memorize in my way, or Chris's way. You don't have to memorize anything. And this works every single time. So it's one less thing you have to memorize, unless you want to memorize.
The P factor is the first one of P, right? That's why it's P1.
Yeah.
Okay. Just make sure.
Yeah, and it goes to P6.
Oh,
And if you count 1, 2, 3, 4, 5, 6. So in the P subshell, you can put 6 electrons. So you can't go 2p7. Then it goes down to the, kicks down to the next one down.
no. Never mind. Yeah, okay. I just want to understand the rest.
Okay, so according to this now, for carbon, so this is core. And these are valence. So carbon has 2, 4 valence electrons. Now, carbon, I mentioned earlier, is a conundrum. It is weird. And I want to show you later on today, I'm going to bring in Star Trek as an example from the second movie. Okay, the thing with carbon, though, it does something called and then it goes something called bond hybridization. Bond hybridization modifies this. Now carbon's the only one that does it. That's why it's a conundrum. Another one that does it is the copper family and the chromium family. Okay, and don't worry about knowing carbon goes through bond hybridization. It just modifies it so that let me back up a second here. The 2 shell has got 2 parts to it, S and P. The S can only hold 2 electrons. The P can hold 6. Okay, the P, because it has 6 electron capacity, is further broken down into something called orbitals. So P really is piece of X, piece of Y, and piece of Z. Okay, when the hybridization happens, all those become one. So according to this S is already full, so it cannot undergo any bonding. The P's are not full because it can hold 6 and there's only 2 in there. So theoretically, carbon has 6 electrons in valence, but only, 4 electrons in valence, but only 2 of those 4 are capable of bonding because the other 2 are very stable. So these are very stable and these are unstable. Okay, so P, remember, as three orbitals, and that's where the 6 electrons are going to go in the 3. So what happens is one goes here and one goes here. Because electrons have a negative charge, as you know, and they don't like to be next to one another. So basically, by putting them in one in each orbital, you're spreading it out, which is more stable. So you would predict that carbon has 2 valence electrons. Carbon doesn't. Carbon has 4 valence electrons. That's where the bond hybridization comes in, is that these things are modified. Okay, so anyway, so as far as if you look up, and only when it bonds, the hybridization takes place. If it's just carbon by itself, this is the configuration. And normally you don't put piece of X, piece of Y, piece of Z, you put them all together. But remember, there are 3 there. D, there are 5. F, there are 7. And they're not along the axes at all. They're goofy looking. P's are pretty XYZ. They're the only ones that look normal. All the rest are really odd looking. And all this comes out in the math of quantum mechanics. It's wild stuff. It truly is. It's okay, so let's do another one. Let's do someone mentioned silicon. Let's not do silicon. Let's do phosphorus. Okay, so we're going to do the journey again through the periodic table. So we're going to go 1s2, excuse me, 1s1, 1s2, 2s1, 2s2, 2p6, 3s2, 3p, 1, 2, 3. So you need to know where the blocks are to do this. And how many are in each block. If you're looking at a periodic table, you can tell how many are in the block. You just count them. Okay, so let's write that configuration down that I just mentioned. We're going to do phosphorus, C, P. Okay, phosphorus has got how many electrons? It's got, you can't see it there, 15 electrons. Okay, so we went through the S's. S's in shell 2. All the P's in shell 2. Kept going. It was 3 over, right? Yeah, 3. So that's for phosphorus. And all that was as we went along the periodic table, and as I went through blocks, electron blocks, I just wrote down what the block is and how many electrons I passed on to that block. Does that make sense? Now, again, I would recommend you either skip that part of the chapter if you've got the book, or just make a note that this is the other way to do it. This is totally unique. My student invented this. I've never seen that anyplace else. Now, many people in the country know this because I've been teaching for a long time. And all my students, this is the way they learn this. Okay, did that make sense what I did? Okay, so valence, core. Notice the core electrons are all full. When things are full, they're more stable because of symmetry. Nature likes symmetry. Now, with that in mind, remember P's have 3 orbitals. There's so those 3 electrons are spread out, 1 in each orbital, because that's the most stable. Okay, but again, we kind of scrunch it together. Now, if I asked you to do an orbital diagram, we would then write little circles or boxes to represent an orbital. So let's look at the orbital representation of, let's see, and those little arrows represent electrons. Notice that they're opposite. The reason they're opposite is electrons have a magnetic component to them. Magnets like to be north to south, south to north, not north, north, south, south. That's why they always are opposite. Now, once you get 2 in there, they kind of magnetic wise cancel each other out. But if you don't have 2 in the orbital, that atom is magnetic. That's what makes something magnetic, is whether you have the leftover electrons paired up or not. So let's continue. Okay, so we have 2s2, 2p sub x, 2p sub y, 2p sub z. And then these are all full. And notice the way I did the p's. I went 1, 1, 1. I wanted to spread that out. And then we have anything left over, we start pairing them up. So, valence, core. So this would be the orbital representation. Yeah, somehow that doesn't look right. Anyway, it's representative representation. So you need to know both those. Now, does this make sense so far? Okay, now I get to throw in a caveat, yet another one. The D's. The D's are slightly different, and the F's are even more different. They're more differenter. Okay, so the D's actually are part of the 3 shell, but they're on the 4th shell line. That's the part that's different. So let's choose iron. So we're going to go 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, 1, 2, 3, 4, 5, 6. And F's are 2 down. I'm not doing S, but so the way I think about it, I go, well, think about D being dumb. So the D's are dumbed down. The F's are fail. Sorry, this is my Chris's way with the children. Remember the F failures. Okay, so let's do iron over here now. We're going to recount our journey. In fact, let's do the orbital one. So we're going to, this will be 1s2, 2s2. Now, when I do the p's, I'm going to put 3 of them in here. And X, Y, and Z. And then 3s2. And I'm going to go down here. Now, D's, remember, can hold 10 electrons. So that's 5 orbitals. That's 10 divided by 2 is 5, right? So that's the orbital diagram for iron. If you take away the orbitals, that would also be the electronic configuration. But the orbitals actually represent what's going on in that atom. So goes the current model. And that model has been around since about 105 years or so. That's when back 105 years ago, Einstein was running around, Planck was running around, Bohr, all these famous scientists. Some of them, they've named elements after him. Like a friend of mine, not a friend, a colleague of mine over at Berkeley, his name was Seaborg. And he used to come to our graduate seminars when I was in graduate school because he found them interesting. And he was part of the Manhattan Project. He helped develop atomic bomb. And there's a element named after him, Seaborgium. And he was a really tall guy. He must have been 6'4"-ish and very soft spoken, really a very nice guy, easy to talk to. And he said he loved graduate students. And our graduate seminars, we had one a week, and we had like 30 or so in our graduate group, and from cross disciplines, environmental toxicology, chemistry, biochemistry, food science, weed science, enology, and the seminar's topics were all varied, and that's what he found interesting. And it was a really cool experience. And very few people, they know about him, but they've never met him, So it was a very nice experience for me. Okay, that's what I wanted to cover on electronic configuration. And this just takes practice. Now the only thing you got to remember are the D's dumbed down by 1. Oh, yeah. Yep. Exactly. Okay. Let's do one more example, then we're going to go to lab. And I've got a worksheet. Let me just jump. Still says record. What? I know, remember I switched because when we were doing the one wet lab, I moved the dry lab the next week down there. So the week of the dry lab, it now became the wet lab. Actually, it was, last week. The gas one. That way it was more consistent. The dry labs you can do at home. Okay, so, I'm gonna show you where the extra practice is. It's in files. And it should be under unit 4. Oh, let's.
For the.
So this is the worksheet.